I'm going to resume the recording now so that if our last couple people don't show up, they can watch this later.
Emmy said her laptop isn't working right now.
Okay. Oh, he just got in. Maybe it's fixed.
Okay.
Thanks, Matt. I think she's in now. Awesome. All right, we're just missing. Okie dokie. So, new unit, thermodynamics. So thermodynamics is all about energy changes. And basically, how do we express this in diagrams, in number values, in like chemical reaction equations? How do we tell the person that's reading about our stuff whether a reaction is endothermic or exothermic, how much energy is being consumed or released? So all of thermodynamics is about the transfer of energy. Okay, because the laws of thermodynamics state that you cannot create or destroy energy, you can only transform it from one form to another. So those of you who have taken some physics and even some bio, you've probably talked about this already. We've kind of already mentioned this already earlier in the year. So basically we're changing the form of energy. In chemistry, we mostly talk about what's called bond energy. Bond energy is the chemistry world of potential energy. Okay, so energy is stored in the bonds of molecules. Okay, and when it's released or consumed, we perceive that as a change in temperature. Oh, I can't. I tried to scroll on my computer. It's not on my computer. That's silly. All right. So thermodynamics. Okay, thermodynamics is the study of energy and the transfer of energy, specifically in thermochemistry, which is what we're doing, okay, is looking at the change in energy or transfer in energy that is involved in a chemical reaction. Okay, so specifically looking at transfer of energy in reactions. Okay, energy cannot be created or destroyed, but only converted from one form into another. So the forms that we're looking at in this, chemical reactions world is potential energy, which is bond energy, or kinetic energy, which is perceived as heat energy. Okay, so we're kind of converting between those two versions. We're making molecules and storing energy in the bonds, and then we're breaking apart molecules and getting energy out in the form of heat. So enthalpy. Okay, enthalpy is something that we talk about in a way of kind of like measuring energy in chemistry. Okay, so it's the heat content of a system, okay, which is basically the sum of the kinetic energy of a system. Okay, so when we perceive something as cooling down or heating up, that is actually a measure, which is why you use like thermometers and stuff when you're doing chemical reactions, of how much energy is being stored in bonds and how much is being released within a specific system. Okay, as a result of molecular motion, okay, of the atoms, because they're always vibrating, okay. In solids, they're vibrating closer together. In gases, they're moving around more. We know that from what we've learned already about solids, liquids, and gases and intermolecular forces. Okay, so the sum of enthalpy of a reaction, okay, is the same way you find the change in anything else. So change in time, change in temperature, change in enthalpy is the same. We take the final minus the initial to get the difference. Okay, so here delta H is the change in enthalpy. Okay, so delta, this triangle shape, is capital delta, that's the Greek letter, and it means the change in. Okay, so let's look at a theoretical example here with an exothermic reaction. So in an exothermic process, okay, given by the general equation A plus B gives you AB plus heat. Okay, we're seeing heat being given out as a product. So what that means is the enthalpy that we have of A plus B separately. Okay, so the energy stored in the bonds of those two individual molecules or atoms, whatever they might be, okay, compared to the enthalpy of the compound that's created as a product, okay, it's greater, which is why we have this excess being released as a product. Okay, so the potential energy or enthalpy in our reactants is greater than our product. So we have this excess energy, okay, being released as heat in an exothermic reaction. So that change, okay, we take products minus reactants, and that gives us our delta H. Okay, so it's the same as our final minus initial, where products are always your final, initial are always your reactants. And that delta H value, which we've actually seen before when we did equilibrium, the delta H value tells you whether energy overall is consumed or released in that reaction as a whole. Okay, so for an exothermic reaction, your delta H is negative, and for an endothermic reaction, your delta H is positive. Okay, which we've seen before in equilibrium, but now we're getting to it again. So there are some calculations that we can do around this, calculating delta H, okay, where we're going to take the products minus the reactants to figure out the overall enthalpy of a reaction. And there's about 4 different ways that we can do this, okay? And so over the course of this unit, we're going to learn those 4 ways of determining our delta H, okay? So 4 ways to find delta H, kind of depending on what you're starting with. So depending on if you're given a reaction equation or you're given data from a lab or other things, this is basically what we're going to spend the rest of the unit doing. If you look at your notes package and you actually scroll to the very end of it, if I go down to the bottom, okay, you'll see the very last page looks like this. So calculating delta H summary. And these are your 4 ways that we're going to learn about calculating delta H. And each one applies in a specific situation depending on the information given in the question. So bond energies we'll do tomorrow, then calorimetry will be a video lesson that we'll follow up with on Thursday. Then Hess's law and standard heat formation after that. So we'll kind of spend a day on each of the 4 types of ways to calculate delta H. So we'll come back to this. This is kind of like a bit of test review type of situation, but that kind of gives you a sneak peek into what we're going to be doing. All right, so going back here, so see, I guess that's page, our delta H summary was on page 14, in case you kind of want to refer back to that at any point. Okay, so Thermochemical equations are things that you're going to be asked to give in all of these types of equations. Okay, and a thermochemical equation is written in one of two ways. Okay, it's either written as an equation with heat written in as a product or reactant, kind of like it was in this equation. Okay, or it can be written with a delta H statement at the end of the equation. Okay, so those are kind of the two ways you can write a thermochemical equation. And the information you get out of this type of equation, okay, is really valuable depending on what it is that you're doing. Okay, so first thing is, let's kind of go through this first example. We're looking at the synthesis of water from hydrogen and oxygen, where the delta H value we're given is negative 436.6 kilojoules. So what this is telling me is that the heat of reaction of water is negative 436.6. Okay, heat of reaction is enthalpy. Okay, so that's the same as delta H. Okay, and so when the symbol is negative, see how this is a negative, okay? If it's negative, that means it's exothermic, right? We already just said earlier that a negative delta H is an exothermic reaction. So we know based on the sign, okay, that it's exothermic. Okay, you also always need to include state symbols anytime you write a thermochemical equation. Okay, that's something that people often forget to do, and they'll just write out the like the products and reactants, and they won't give state symbols. But the enthalpy of a reaction, like your delta H value, actually changes if things are in different states. So you have to include the correct state for the particular delta H value that you're looking at or talking about. Okay, so they must be included anytime you're looking at writing out a thermochemical equation. Okay, and the last thing is that your reaction always needs to be balanced. Okay, so you'll put in coefficients to make sure that your thermochemical equation is balanced, because delta H is given per mole when it's put into an equation. So if you're ever converting between like this type of reaction where it's given a delta H value based on a certain coefficient, and you switch over and you go to writing it into the actual equation, okay, if it's in the equation given as a product or reactant, it needs to be kind of included in the balancing part. So it needs to be given per 1 mole of whatever it is that you're talking about. So let's go through an example of, a type of calculation you could do around thermochemical equations. Here we've got how much heat is evolved in the thermite reaction. Okay, so if we were in school, we would actually do the thermite reaction. Some of you may have seen it before. Dr. Melville likes to post videos sometimes of him doing it, where you take iron oxide and you react it with aluminum, and it's crazy hot. It lets out like so much energy, and you get this like molten iron. He always does it outside. If we go back to school, even if it's after this unit is over, like this module, I can do it at lunch sometime and show you guys, or we'll watch a video maybe, but we can't unfortunately actually do this in person, which is too bad, but is what it is. All right, so thermite reaction. When 225 grams of iron oxide is used in the reaction. So here we're given a certain amount of one of our products. Okay, so our mass here, 225 grams. Now remember that everything is per mole. So we need to convert our grams into moles. Otherwise, we can't convert from the amount that we're starting with to how much energy that's going to produce. Okay, this question wants us to determine, based on this reaction equation, how much heat, okay, or what is the kilojoules, okay, it wants kilojoules of energy that's going to be released when we start with 225 grams. Okay, so 225 grams, we're going to convert from grams to moles because this is in per mole. So we're going to use unit analysis the way that we did in grade 11. We've seen this before. Okay, 225 grams of iron 2 oxide, or iron 3 oxide, pardon me. We're going to convert from grams into moles. Okay, and the way that we go from grams to moles is using molar mass. Okay, so we're dividing by the molar mass of iron 3 oxide, which happens to be 159.687 grams per mole. Okay, so in terms of sort of annotating what we're doing here, we're taking the mass, we're converting it to moles, okay, by dividing by the molar mass of whatever the thing is. Anyone have any questions so far?
The molar mass, did you use like 2 of Fe or just Fe?
2. So the molar mass, I added up 2 irons and 3 oxygens. All right. So once we know the number of moles, so now we have moles, we can use our delta H value to convert from, based on that amount of moles, how much energy or heat is actually being released in this reaction that's involving this much iron 3 oxide. So now I'm going to multiply again. I'm using unit analysis to drive like the direction of my calculation. I have moles on the top now, so I'm going to put moles of Fe2O3 on the bottom. And I want to find kilojoules, okay, of heat. And the thing that's measured in kilojoules per mole is my delta H value. So I'm going to put this number in as a conversion factor to convert from moles to energy. Because my delta H value is telling me that for every 1 mole, okay, I'm releasing 822.8 kilojoules of heat. So if I have 225 grams, which is going to come out to be, 2 moles or whatever it is, how much energy are we letting out? So I'm going to put that number in. Okay, and I don't want to forget the sign. So I'm going to include that negative 822.8 kilojoules per 1 mole. Okay, that's going to cancel out, just like the grams canceled out before. So in this step, I'm using delta H to convert moles. So I'm using it as a conversion factor, okay, to kilojoules to figure out how much energy. Okay, when I go through and I actually do the math, I take 225 divided by 159.687, and then I multiply that by negative 822.8. I'm going to get negative 1159.33 kilojoules. Okay, that's the unit that I have left over at the end, okay, which is our heat. Okay, and that negative symbol is telling me that it's exothermic, so it's telling me that that amount of energy is being released. Okay, so the negative equals exothermic. Okay, energy is released rather than like being consumed. Okay, any questions about what we did there? So next we're going to look at potential energy diagrams, which you may have drawn before in chem. You may have seen them. Actually, I'm trying to think of when we may have done them at some point. But if you've taken physics, you've definitely drawn this type of thing before. Even in bio, you've probably seen it if you're taking bio. But potential energy diagrams are a way of showing how much energy is being stored, released, absorbed in any kind of process. So it could be, in this case, because we're talking about thermochemistry, we're looking specifically at potential energy diagrams of chemical reactions, but you could draw a potential energy diagram of a roller coaster or of a car going up and down a hill or anything like that. So it's the same idea as those other ones that you've probably seen before, but we're specifically looking at reactions here. Is everybody okay if I move the slide along or the paper along? Okie dokie. So we'll look at each one individually first. So we'll do endothermic reactions, then we'll look at exothermic reactions. Okay, kind of as a summary of both. So first of all, endothermic reactions. We want to keep in mind overall with all of our reactions, okay, that energy, you have to put energy in to break a molecule apart because there's energy stored in the bonds. So it's stable and happy the way it is. And to disrupt that stability, you have to put energy into it. Okay, but then when you make new bonds, okay, it becomes stable again and energy gets stored in those bonds. Okay, and so you get energy out because it's kind of like it's relaxing. Okay, so there's a little memory trick that we can use to help us. Okay, we break into the bank and we make out with the cash. Okay, if you're in any of my bio classes, you've seen this phrase before. Okay, break into the bank, make out with the cash. It's just a little like memory phrase trick to help you remember that to break bonds, you have to put energy in. Okay, so to break bonds, okay, you have to put energy in. And when you make bonds, okay, you get energy out. Or energy is released.
Which Roseboro?
Yep.
Which one is anabolism?
Well, anabolism and catabolism are a little bit different. It's not exactly the same because that's looking at like a metabolic process rather than like the simple act of like making and breaking molecules. So like anabolism is like making polymers and catabolism is like breaking apart polymers. It's not quite equivalent. But that's a good connection because yeah, you're right on the money with that one. It's exactly what we were talking about in bio. Okay, so endothermic reactions, we'll start there. So in an endothermic reaction, okay, the bonds that are broken, okay, the energy that's absorbed is greater than the bonds, than the amount of energy released when the bonds are made. Okay, so the energy absorbed to break the bonds, or the energy needed that has to go in to break the bonds, is a larger amount than the energy that gets released when new bonds are formed. So we've got a couple of examples of a thermochemical equation here. Okay, again, this is sort of just to give you an example of the two ways we can write this equation. So the first way, we can write in our energy as a reactant. Okay, so in an endothermic reaction, energy is a reactant, or it's given as a positive delta H value. Okay, so energy is a reactant. Okay, or your delta H value, okay, is positive for an endothermic reaction. Because the overall change in energy, okay, you're going to see when we draw the diagram is like a positive change. It goes up. So let's draw ourselves a diagram. Okay, so you're going to draw an arrow with an E for enthalpy. And when you have an endothermic reaction, the amount of energy that you have to put in always has to be greater than whatever you're getting out. So you want to start really low with your reactants. Okay, you have to put a bunch of energy in, okay, to actually break the bonds, okay, of those reactants. And then you're going to get some energy out when you make products, but not as much. So when we go up in the diagram, that's energy in. And when we go down in the diagram, that's energy out. So now when we compare the enthalpy of our reactants and the enthalpy of our products, okay, we're going from here up to here. So we're going from lower to higher. So that's where our positive number comes from. Okay, so we get a positive delta H value. All right, so this slope, as we go up the hill here, okay, represents the energy in to break the bonds of the reactants. And the downward slope on this side represents the energy that gets released. Okay, when the new bonds are made. So hopefully you can see in your diagram, okay, so it doesn't matter if it's like perfectly like to scale or anything, as long as you can see a difference, okay, and your reactants are lower, they have a lower potential energy than your products, and you had to put more energy in, so your upwards line, like your upward slope, is bigger than your outwards, like your downward slope on the other side. Okay, and the higher something is on your diagram, the more potential energy it has. Okay, so let's make a side note of that. Okay, the higher something is on the diagram, okay, the more potential energy. Okay, so in this particular example with an endothermic reaction, okay, our products are higher on the diagram, which means the molecules that are in the orientation of the products have more potential energy. There's more energy stored in the bonds of the products than there was when they were in the orientation of the reactants. Okay, different types of bonds have different amounts of energy associated with them. We're going to talk more about that tomorrow, but every bond depending on if it's a carbon-carbon bond, an oxygen-hydrogen bond, they all have different potential energies, which we call bond energies in chemistry. Okay, so the products have a higher potential energy than the reactants, okay, when it's an endothermic reaction. Any questions about that before we look at exothermic reactions? Okay. Exothermic reactions are the same but opposite. Okay, so it's all just pretty much exactly opposite. Okay, in an exothermic reaction, the amount of energy absorbed is less than the amount of energy that gets released afterwards. Okay, so this time more energy is going to be released. So the downward slope of our diagram is going to be longer or bigger than the amount of energy that you have to put in at the beginning. Okay, again, you can draw your thermochemical equation with either a negative symbol in your delta H value or your energy drawn in as a product. Okay, so with endothermic reactions, energy was a reactant. With an exothermic reaction, energy, okay, the change in energy is a product. Okay, or you're writing it in with your delta H value as a negative symbol. Okay, and we'll see where that negative comes from when we draw our potential energy diagram. Oops, sorry about that. So you can draw in your axes for energy. You can draw in, if you want to put an x-axis in this way, this is just progression of the reaction. If you want to draw that axis in, but you don't really have to. If you're drawing a potential energy diagram, you really only have to write in your y-axis. Okay, so this time, because more energy is being released than goes in, we want to write in our reactants higher up with a greater potential energy than our products. Okay, so it's going to look like the opposite shape as our endothermic reaction. So I'm going to start up here with my reactants higher. I'm going to put some energy in to break them apart, right? Break into the bank, make out with the cash. And then we're going to get more energy out as we form products. Okay, so this time, when we compare our reactants and products, right? We started at reactants and we're going down. That's where the negative comes from. So delta H, oops, I forgot to write the negative in. Negative change in enthalpy or negative delta H value. Okay, so this little upward slope again represents the energy put in, okay, or absorbed energy in to break the bonds holding the reactants together. And on the other side, our slope coming out, that big long downward slope represents the energy released. Okay, when bonds are made to form your products. Okay, so you're getting more energy out than you had to put in. That release of energy, okay, would be seen as basically like a release of heat. Okay, for an exothermic reaction, your reactants contain more potential energy stored in their bonds, which is why we can release more energy when we like make them into something else. Okay, so sort of like what we did with our endothermic reaction. Okay, we're going to quickly identify here that the reactants, okay, because they're higher on the potential on the energy diagram, right, than the products, they're higher up. Okay, reactants have higher potential energy. Okay, than the products. In an exothermic reaction. Okay, and that's where we're going to stop our lesson for today, but we are going to do some practice. So we have 20 minutes left, which is plenty of time for us to do the practice questions listed below. So here are the practice questions. I have them, I'm going to project them on the screen. If you have your textbook with you and you want to open it up, feel free to do that. I'm going to give you guys a couple minutes to try a few of them on your own, and then I'm going to take them up. And I will, yeah, I'll show them. You can either open them on your own computer if you want, or I'll show some of them on the iPad. And my computer's just dying, so I'm going to grab my charge cord and then I'll be back. But let's give some of these a try. Okay, so thermochemistry practice. I wonder if I can, I don't think I can adjust where things are. If I show 6, 7, and 8, are they too small to read the questions, or can you read it? It's a little bit small, but. So just grab a piece of scrap paper. Okay, I'll leave those ones up for now. Actually, I might be able to do. Can I do the, is it this the thing where I can cut something out? Put it like there, and then can I zoom in more? Oh, look at me being all fancy. There, hopefully that's a little bit easier to read. Okay, so I'll show these ones for a couple of minutes, and then I'll switch over and show you guys the other questions because I have them as well. And then I'll take them up in like 10 minutes. So try a few, see where we get to.
Ms. Roseborough, when are we getting our chemistry tests?
They'll be up by the end of the day. You may have actually noticed I've marked about half of them. But because I have to take all of the pictures that you sent me, put them individually into a Google Doc, import that Google Doc into Notability, mark the test, and then turn it back into a Google Doc to share with you, it's kind of a long process. So I'm about halfway through marking. So some of them you might see like your mark is in Edsby already. And some of them I haven't marked, but I will post like all of the feedback and everything as well. So I'll finish that up later this afternoon. So hopefully by like dinner time, I'll be all done and I'll have posted all of the like the feedback, like the marked up version of your test.
Okay, thanks.
You're welcome. Okay, I'm gonna switch the screen over, okay? So I'm gonna show the next questions. If you didn't quite get through those ones, that's okay. Just move ahead. We'll come back to them if you didn't quite finish. Hopefully you can read that okay. Okay, I'm gonna leave this here for 5-ish minutes so you can try some of those questions. Just do what you can in the amount of time, and then I wanna save myself at least 5 minutes to quickly take them up. They're not very long. So give them a try for a few minutes and then I'll take them up. Okay. Just a quick reminder that in general, you are supposed to keep your video on in class. If you need to turn it off for a moment while you like blow your nose or something, you don't want everyone watching you, then that's fine. But for the most part, okay, unless I specifically say like it's cool to turn it off for a while, please leave your video on so I know you're actually doing chemistry work. Otherwise, I'm gonna assume that you're like, I don't know, eating breakfast and watching television and not actually paying attention to chemistry. Okay, I'm gonna start to take some of these up. I'm sure like if you may not be done all of them, that is totally fine. We can take a look. If we don't get through taking them all up before 12:30, then whatever ones we don't finish up in these next sort of 7 or 8 minutes, we can start off tomorrow in class taking up the last few questions. But I wanna make sure that we take up a few in case people are a little bit lost. So I don't know how to get rid of this now. Oh well, okay. Number 6, a compound such as calcium carbonate, okay, can decompose by absorbing energy. This reaction can be written as shown. So here we're given a reaction equation where energy is written in as a reactant. Okay, so A, identify which has the greater potential energy, the reactants or the products. Okay, and B, is the enthalpy of the system increasing or decreasing? Is it endothermic or exothermic? Okay, and is energy change positive or negative? So the best way to go about answering this question is actually to draw the potential energy diagram of this reaction. Though we don't have any specific numbers, we can still get like an overall rough idea of what this should look like. Okay, so here I'm gonna do it, I guess below over here. So here's my, okay, energy axis or my enthalpy axis. If we have to put more energy in, energy here given as a reactant, that means that this is an endothermic reaction. So the shape of my potential energy diagram is gonna be like this, okay, where our reactants are over here and our products are up here. Okay, we're putting this energy, more energy in, okay, than we are getting out. So for A, what that means, okay, A in green, is that our products are gonna have a higher potential energy. Okay, because they're higher on the list, there's more stored energy in those. If you were to reverse that arrow, okay, if we look at this reaction equation again, if we were to reverse this, okay, we would be getting energy out. So there's more stored energy in the products orientation of those atoms, okay, that would be released than in the orientation of the reactants of those atoms. For B, is the enthalpy of the system increasing or decreasing? Is the reaction endothermic or exothermic? And is the change positive or negative? So here we've already determined that it's an endothermic reaction because energy is being absorbed. Okay, it's one of the reactants. So we already know that that's the correct version for that one. Okay, so here on our diagram, we're comparing the change in energy between reactants and products. We're going from down here up. So that's a positive delta H value. So it's endothermic. Delta H is positive, okay, which means that the enthalpy of the system is increasing, okay, because we're going up. The arrow is upwards, increasing. Any questions about number 6? Okay, let's take a look at number 7. So for number 7, the standard molar enthalpy of combustion, so delta H, of a hydrocarbon is always a negative value. Okay, so that's basically saying in any combustion reaction, like we saw in grade 11, right? You're always releasing heat and light, right? When you burn anything, you're getting energy out. Is the enthalpy term included in the as a reactant or a product? Okay, in the thermochemical equation of combustion reactions, how do you know? So here, if the delta H is negative, Okay, so here this is telling me that we have a negative delta H. Okay, that means that energy is going to be released. Okay, so if energy is released, it's an exothermic reaction. Okay, this is like burning alcohol or burning butane in a camp stove. Okay, that's the type of reaction that we're talking about here. We have a negative delta H value. Energy is being released. It's exothermic, which means that energy would be written in your thermochemical equation as a product. Alrighty, question number 8. For the reaction shown below, which has more potential energy, the reactants or the products? State your reason for the choice. So here we're looking at this reaction. We've got methane plus oxygen forming carbon dioxide and water. So this is combustion of methane. Here, whoa, I just dropped my pen. Here we have energy written as a product. Okay, energy is written as a product. That means it's exothermic. So if we draw a potential energy diagram of an exothermic reaction, okay, it has that shape, reactants and products. Where your delta H value, we're starting here and we're going down. So we have a negative delta H. Okay, what that means is that there's more energy stored in the bonds of the reactants than there is stored in the bonds of the products. Remember, bond energy is a type of potential energy. It's stored energy. That's what potential means. So there's energy can be divided into 2 categories, potential energy and kinetic energy. Okay, so potential energy in chemistry is bond energy. It's the energy stored in those bonds. So whichever thing, reactants or products, is higher up on our energy scale, okay, is the thing that has the higher potential energy. Okay, more energy stored in the bonds of those molecules. So here are reactants. Okay, the question said reactants or products, so the answer is reactants. Okay, is a higher potential energy. Reactants have higher potential energy.